Hi, everyone. Thank you so much for joining our session. This is a session being chaired by the ESDIS Standards Coordination Office at NASA in the Earth Science Division. We are the group that kind of receives proposals to adopt standards, and we facilitate community reviews and make recommendations. Steve Olding will tell you a little bit more about us in a minute, but we have, over the years, adopted many standards for NASA data products, and it occurred to us that maybe we need to do more to make it possible for our data producers and our data publishers, which are NASA data centers, data active archive centers, NASA DACs, we call them, to make it easier for these groups and others to standardize data. And so we wanted to look around and see what kinds of tools currently exist for standardizing, making data standards compliant. We get a lot of data in that is not terribly standards compliant. It's getting better. We're getting a little bit better at talking data producers into paying attention to standards, but still we have a lot of data that isn't standards compliant. And how to get it there was a question that we asked ourselves. And so we started looking around and thought, hey, let's have an ESIP session and hear about some tools that are out there for taking data that may be standards compliant in one format, but needs to go into a GIS tool or something and be transformed. And so we're looking at a lot of different tools, how to facilitate standardization of data. Or we've got a lot of NetCDF data that's not ready for the cloud, and making it cloud optimized is a big goal for us. And so we want to hear about how we might be able to do that with the petabytes of data that we have that are not yet cloud optimized. And so that's what this session is about. We're going to hear from a few presenters first, and it's a somewhat informal session, and that's totally on me because I'm a procrastinator and a last minute person, and so I didn't get organized in time to get a lot of organization for this session, but we do also want to follow up the presentations with some discussion about what are the gaps. Right now we do have some tools for making data standards compliant, but what do we need to have, and what should we be working towards, and how can we get there? So that will be the second half of the session, and we're going to go ahead and start with Steve Olding giving us an overview of the ESCO office and what we do. Steve, go ahead.
Okay, I've got how do I get my PowerPoint into like a presentation mode? There's a button.
Steve, I put yours into the Google Drive.
Oh, do you want to, you present it from there? That'll,
You want me to grab it? Okay.
yeah, that'll.
Let's see here. Do you want, I'm going to do the PowerPoint or the PDF, because is it okay if I show the PDF?
Yeah, it should be the same.
Okay. No, that's not what I wanted to do. Where is my screen? Am I able to share from?
You should be able to share screen. It's at the bottom.
Yeah, I see it. Okay.
Yeah.
It's just blurred out my screen. You're not seeing it, are you?
No.
It's
Okay. Do you want
just,
me, let me try. I'm going to do this with a different. Let me do this with something else.
yeah, sorry. I am on my NASA computer. I wonder if it's stopping me from sharing.
Okay. Let me.
But now I'm stuck in this weird blurry mode.
Okay. Are you seeing my screen?
I see something, Steve.
Yeah, I'm seeing your slides, Steve.
Okay, sounds good. So yeah, as Beth said, we are ESCO, the ESDI Standards Coordination Office. Like the name says, we coordinate standards for NASA Earth Science Data Systems. I'm Steve Oding, the lead for the group. Beth and Ed also on this session are also part of the standards office there. So I'm just going to go over sort of briefly kind of what we do, how we do it, as a kind of an intro to some of the things we're currently looking at. It's kind of one truism about sort of standards that I'm not, they say the nice thing about standards is that there are so many of them to choose from, and that's the joy and the pain of standards. One of the things that we, in our science discovered a long time ago was everybody was choosing their own favorite standard, but not everybody was choosing the same one. And that's sort of how the Standards Office came about, to provide guidance on which standard to choose, so that every mission, every project wasn't using something similar but different. So trying to sort of coordinate all of that. So sort of things we do, we maintain a list of the approved standards for use in NASA Earth Science Data Systems. We also maintain a sort of list of guidance. I think what a lot of people find is some of the raw standards documentation is pretty heavyweight and kind of hard to comprehend. Often what they need is guidance on how to use a particular standard on their project. So, there may be a general standard, but there's additional guidance on how to apply that within the Earth science data context. So we have information of that sort of type as well. We manage the ESDI standards process, so we have a formalized process for how to go about getting a standard approved, and I'll say a little bit more about that in a moment. Part of that includes the formation of something called technical working groups, so we organize and run those. And we work with ESDIs and external standards organizations to identify future candidate standards. So it's not just, what are the current ones? We're constantly monitoring what's out there and saying, well, should we be looking over here? This seems to be emerging as an important area for standards. And then the last part of that is communication of that. So mostly that's through the Earth Data website. So we've got a section on there dedicated to standards that we maintain. That'll list all of the things that we've approved or in the process of approving. So this, very briefly, is our standards process. Anyone within the NASA Earth Science community can propose a standard for adoption. We do an initial screening of that, making sure that it's, has some meets some basic criteria. If it satisfies those basic criteria, we make sure it's readable, it's got all the right, included all the right documentation. Then we would send that out for a community review. So we would look to, we've got some people that we've recognized as being the sort of people responsible for standards in different areas. So like at the different DACs, we also have sort of contacts, subject matter experts in particular areas that we might call in. So we would run a community review, usually running from sort of 2 to 4 weeks, which would allow sort of feedback on that proposal. We'd have following that review, we'd have an appraisal of the sort of feedback that comes back, whether there's a general consensus, whether there are things that people are particularly objecting to. If everything works okay, then we would work with the author to edit that document accordingly and then publish that to our website. If there were too many, I guess, kind of critical reviews, then we may go back and rewrite and kind of go through a second round of community review. So we're basically looking for a sort of community consensus that whatever we're approving is going to work in the NASA Earth Science community. Oops. I'll just put this slide in here because one of the things that seems to confuse people is these requests that come in, we just refer to them as RFCs. It comes from the term request for comments. And this was the ESDIS standards process was modeled after the Internet Engineering Task Force approval process. And we just adopted the term request for comments, which is what they use. So that's what RFC is. Very briefly, this is some of the things on the left that we've recently worked on, and on the right, we're currently or expect to be working on in the next few months. So last year we approved RINEX, Receiver Independent Exchange format. It's a data interchange format for raw satellite navigation system data. That was kind of a legacy thing. That standard had been in use for a while, but nobody had ever sought approval for it. So technically it was not ESDIS compliant because it was a unapproved standard that was in use. So that was really a retroactive thing to go back and get that approved. We approved the third part of the dataset interoperability recommendations for Earth Science from the ESDSWG working group. This is the third set of recommendations they produced. This was one of what we used to call the Earth Science Data Systems working groups. They work on some of the nitty-gritty of implementing standards in the Earth Science domain. So, often we find there's ambiguity or inconsistencies across projects on how a particular standard is implemented. That's one of the things that this working group has been looking at, is kind of clarifying some of the areas where there's room for ambiguity. Data use and citations guidance, there was an update to the ESDIS published guidance on how to cite NASA data, so we were involved in the review of that. And WGOS unit notation, the World Meteorological Organization Integrated Global Observing System code list. So, it transpires there are multiple different ways of writing down certain units of measure. One of the ones that caused particular confusion was the mu character. There are at least 3 different ways of having a mu character, and using things differently across different projects causes room for confusion and ambiguity. So standardizing how we write down our units of measure is one way of addressing that. So that's the WGOS unit notation. Coming up, we've got soon to be published the guidelines for citation. Let me step that back. We're looking at guidelines for the citation of airborne facility instruments. What that's brought up is some issues around guidelines for complex citations. So the issue there is both the data set and the platform, or the facility instrument that produces the data, and how we cite complex use cases. So that's probably not coming soon because it's brought up some bigger issues that we need to address first. So, but that's one of the things we're currently looking at. What is coming up very soon is the practical guide for open, free, and fair NASA Earth Science data products. That's recommendations from the ESDSWG OFAIR working group, and that is very nearly ready to be published, so like within the next week or so. Coming up later this year, so some of the things we're starting to look at, SAR version 3. So SAR version 2 has already been approved. There's some changes to create the version 3, so we need to put that through our standards process. And STAC 1.1, so version 1 is already approved. There's already a version 1.1 which includes a few changes that we need to look at to get that version approved. So just very quickly, this is where you can find us. So we're on Earth Data. Just search for ESCO or standards. You'll find us. There are a couple of links there. We're always happy to have more people involved. We'd like to know who the people are in the Earth Science community who work with standards. Happy to talk to you. you can email us at escostaff@list.nasa.gov. We're pretty much always at the ESIT meetings. You can find one or more of us here. We're interested to know about any best practices, lessons learned, specifications that are important to your mission. Are there gaps in what we have there that we could help with? Also happy to have volunteers review for our technical working groups. As I say, if you're working in the standards area for your project, you'd be a good point of contact for us to, if we're doing a review, send out to you for your comments, or get you involved in one of the technical working groups. And even if you're not actively involved in that, please use our documents, our recommended standards and guidance. And I think that was all I wanted to go over. Thanks, Beth.
Awesome. Thank you, Steve. I want to just go ahead and jump right in. If you guys have questions about ESCO, let us know. But in the interest of time, I was going to go ahead and jump in with the rest of the agenda. And Steve went over some of the standards that we've approved in recent times. And now we're going to be hearing from speakers who have tools for some of those standards, for how to work with some of the standards that we've adopted. So let's see what we've got here. Julius, I've randomly put you first for Ice Chunk. So if works. You could, do you want to share your own slides, or do you want me to try to do it?
Let me see if this works again.
There they are. I see them. Okay. Oh. Perfect. Why don't you do it, or whoever's got the, thank you for the speed with which you pulled those up.
Thank you. My name is Julius Busecki. I'm a recovering academic. I used to work at Columbia University and Princeton for a little bit until last year, and I'm now a freelance consultant. I've worked with Development Seed for the majority of last year. This is most of the work that I will be presenting, but I've actually just today started with Earthmover as a consultant. But that's enough about me. What I'm going to talk about today is, I think more of an sort of like some stories about implementation of the standard, in this case, ZAR v3, using a concept called a virtual ZAR. I'll explain that in a little bit, and particularly using IceChunk, which is the open source storage engine by Earthmover, or made by Earthmover, but increasingly also a community project. I just wanted to thank Ed for inviting me to this session. Sorry if things are a bit rushed. I came right from vacation and made those slides in the last 2 days. So just a quick sort of motivation. I think this is how I'm thinking about a lot of these data sets. First and foremost, it's always amazing to see that a lot of the Earth science data is just freely available, right? Like, we always got to note that. But I think we also got to acknowledge that things are difficult to use. I think this is just sort of some example. Some random user wants to take data set A and B, and first of all, they're like in different formats. Let's say one is HDF, the other one is GRIB. There's a bunch of others, and then they're organized in a different way. So, like, for every new data set, you basically get the similar task of needing to understand how the data is saved out in individual files, and then sort of how to read and parse those files. And on top of that, this is not very cloud optimized in some of these cases. So if you're building a service or web app that wants to use this data, it might not be the most performant way to use the data. I think worst thing about this is that the friction really scales to every user. So every single entity that wants to use the data has to overcome the same issue. So it's very, I think, a strong motivation to sort of push some of that complexity back up and let the user have an easier experience. Because I think in my experience as sort of like a oceanographer by training, but then also sort of over years becoming more of a software developer, you see people fix this, but they fix it in a way that is then not intercompatible or very specific to the environment they're working in. And in the end, what that creates is a ton of technical debt and incompatibility, and people just repeat work. And I think in the end, what that means is the scientific community, and even the extended scientific community, everybody who wants to work with that data, is wasting a ton of time. And if because of that, data remains underutilized, and the science really and downstream developments are slowed down. That's how I usually view the motivation for these things. So ZAR has emerged as a standard to alleviate a lot of these pain points. Well, I don't want to really say recently, but in the past years, and sort of some of the advantages of exposing data as a ZAR store is that it exposes a data cube, and I'm always sort of hammering down on the idea a data cube is a scientifically useful unit. A file is not. A file is an attribute of how the data was produced. So as a data user, a scientist, or someone else who wants to use the data, having everything that you want to see from a single variable in a cube is a more natural way to look at the data. Then ZAR is also chunked for either parallel access or accessing just the chunks of the data that you want to look at. It separates, and this is sort of the cloud optimized part of it, it separates the metadata from the actual data. So you can very cheaply, with a few requests, load all of the information about your data and how it's laid out, and then use only those chunks that you actually need. And I think like in the past years, I've definitely seen that users want this kind of data. This is not just something I think that people want to sort of manifest. I've heard this time and time again, how much easier it is to load data in this way, how much more performant it can be. And so I really think there's a push for that. But I think up until recently, until we became IceChunk, or maybe I'm jumping ahead of myself a little bit. Let me introduce IceChunk here. I didn't actually rehearse these things. But so IceChunk now is basically is a storage engine. That's what it's called. That sits in between the ZAR library, which presents sort of the API, the data access layer, and the actual storage layer, which is either object storage or a file system or even memory. But for this mostly for testing cases. And what it does, I think it adds some features that are necessary to sort of make the ZAR experience more production ready. And the most important things are that it adds a snapshot and tag functionality that's similar to Git, and it adds ACID transaction. And so you can present the user with different versions of the data. You can have different branches of the data that have like a different level of, let's say, post-processing on the metadata, or sorting things in time, for example. And you can sort of tag data, so you can time travel and know exactly which version of a given data set you're actually using. This is particularly important for data sets that are continuously updated. The other thing is also you can write to the same store that other people are concurrently reading from. I'm not going to do a demo this time. I've done this successfully in the past, that I've added some new data while I was computing a mean over the entire thing. And I think this was really sort of the key to unlock what I'm always calling like having your cake and eating it too, is this in the time before IceChunk and before the idea of virtual ZARs. IceChunk is just one implementation of that. So a virtual ZAR store is basically something that the user can access as a ZAR store, but it actually points to data somewhere else. And in reality, this is something called a chunk manifest that basically just points to a file somewhere and gives an offset and a length to get just that byte range from that file for a given chunk. And Max is going to talk a bit more about the details of this later. So that's just my high level explanation here. But yeah, it basically sort of completely eliminated this conversation that I've had about 100 times. It's like, should we switch to ZAR, to native ZAR as an output, and with that sort of break backwards compatibility for other folks who have already invested time into file-based workflows or are very happy with the file-based workflows in a particular environment? Or do we duplicate our storage efforts? This is basically what I've done as a side project for several of the last years, is just copying CMIP6 data into native ZARs, and thankfully, we had free storage from the Google Open Dataset program. But for any kind of other effort and big data sets, this is a real blocker. And with virtualization, you can really get the best of both. And so virtual ZAR really is just Yeah, it's a collection term for a storage engine that is compatible with Zar. In the Python world, we currently have two options for the storage engine: Kerchunk and IceChunk. There might be more coming up, but I personally, at this point, strongly recommend using IceChunk because Kerchunk has a couple of things that really make it, in my opinion, not production ready. In particular, the fact that Kerchunk files can't be written while other people are reading it. So you'll always have a small amount of time when you're actually overriding and breaking people's workflow. The one thing that has to be pointed out is that this virtualization is not a new thing. This builds on sort of like shoulders of giants, as always. There's been a lot of work and a lot of the newer technology to make this even easier to build and maintain. This has been inspired by a lot of previous work. So I just want to give some credit to that. The last thing I want to say sort of from user experience is this is not just more user friendly in the sense that you're getting to quickly open things and stream data. Using IceChunk as the storage engine has, in many of the cases that I've worked on over the past year, just automatically right off the box increased the performance because the I/O backend is written in Rust. And I think then if we're thinking about scaling this, it really makes it much easier to serve big data sets to many people in a simpler way. So basically, the dividends of making a virtual store for an existing data set or a new upcoming data sets will always basically scale out to all of the users of that data set. So I think it's particularly important to consider this for very popular data sets, which not only will make the users have an easier time, but it will also, as I said before, make sort of the products that people write more intercompatible because they don't have to implement sort of custom workflows to deal with the files themselves. And yeah, Max is going to tell you more about this. I just wanted to quickly run through a couple of the things I've built at DevSeed and just give you a little overview here. And you can look at the links that I'm hopefully showing a little later here. So there was the RASI and the NLDAS data sets. These have a low update frequency. And for sort of a first prototype, we have just implemented a simple script that basically converts files into a virtual. And we have then actually manually copied the IceChunk files to a public S3 bucket. All of these stores were built on the NASA Veda Jupyter Hub and then transferred manually. And the good thing about these is both the IceChunk stores as well as the original files are on public access buckets. So you can actually run this code if you're interested in this from pretty much anywhere where you have access to the internet. The other data set that I've worked quite a lot of time on is the Muir SST data set. This builds on a lot of work actually that was done by in collaboration between NASA Development Seed and Earthmover, if I'm quoting this correctly, and a bunch of my amazing colleagues. And what I've added to this is basically an AWS Lambda-based updating mechanism that for like on a given regular time trigger searches for new granules, adds them to the IceChunk store on a development branch, and then runs a couple of consistency tests just for an example, whether there's time steps missing or if they're misordered. And only if these tests pass, it merges it into the main branch. And at that point, a user can basically get the new and updated data. Just as an example here, just running the same analysis workflow was 15 times faster afterwards than compared to opening it with just FSSpec and OpenMF dataset with Xarray. The other thing that is cool about this, and this comes back now to standardization, is that all of these data sets, I basically wrote the support for virtual IceChunks into T-Tiler Multidim. And by virtualizing all of these data sets, basically you can now pull up all of them in a Tiler app like T-Tiler Multidim, and they're all supported at once without having to implement any dataset specific logic. That is all sort of absorbed into the virtual store building. And I borrowed this from Max. I think that's sort of the ultimate vision board that we had over the last year, is sort of establishing Zar as the standard that both science users and applications actually sort of see. So they don't have to worry about all of these other parts down. Well, I guess this is to the right, whether that's upstream or downstream, I don't quite know. I guess upstream. And then basically the virtualization of different file formats handles the standardization on that layer and saves a bunch of work down the line. So now everyone can build a virtual IceChunk repository when you have access to the source data. But I think there's a strong point to make for this to happen as close to the source as possible. I think trust is the first one that I'm thinking about. Basically having both the source data and the virtual representation of them hosted by the same organization makes it easy for people to decide on whether they trust that organization, and they don't have to sort of go through all of the provenance and see which part of those things they trust. The other practical implication here is you cannot just blindly trust these sort of misdirected links. You have to explicitly, as a user, agree to and vouch for a location where these are from. And so in the case where you have all of this contained, like for instance, at the NASA Earth Access Library, we could very much simplify the code that is needed. So on the left, you see a bunch of lines. All of this is really just authentication that you need for your virtual store to access the source data. For these sort of tighter scoped and sort of organization-specific data sets, you can drastically reduce that. This is work in progress. It's not quite working yet. And then I think the obvious reason maybe is like data producers are likely in the best position to know about the data in general and know about the quirks. And so this is just a plea for pushing for sort of virtual store production close to the source, meaning with the data producers. I've just summarized these. Happy to take any questions. And if you want to contact me, I think GitHub and email are these days probably the best. Maybe LinkedIn, not so much on social media anymore these days.
Thank you, Julius. That was great. Are there questions immediately? I'd like to actually have Max go next, even though that's not how they're on the list. I think it makes sense for Max to go next. And also, just for when we finish with the presentations and we're moving into discussion mode, I want to tee up sort of virtual Czar and tools for working with Czar formats and that sort of thing as a discussion point. I've got some questions, and I'm not going to ask them right now because I want to have a larger discussion later at the end of our session, and so I'm going to hold that. But are there others that have questions and that are sort of specific to what Julius just said? All right. Oh, Micah?
Yeah, I can. This might be a quick one. Thanks for the talk, Julius. Enjoyed it. So my office is looking at implementing Virtually Czar and IceChunk, but we're running into a specific problem with the requirement for, I believe it's like uniform chunk sizes. And I'm wondering if you've encountered that, and if you had any thoughts to share about, the path forward for that particular topic.
I've certainly encountered that. I think Max might touch on that, and I think it's either already fixed or very close to being fixed, but I'll leave it at that and defer to Max.
Micah, I don't know if this is relevant to your question also, but Dean is going to talk after Max. So Dean, you're going to go after Max just so you can prepare yourself if you want.
I don't do anything with variable chunk sizes though.
Okay.
Address Micah's point.
Okay.
Well, I think I'm in the right session then. So thank you. Thanks for.
Yeah. Cool. All right, Max, why don't you go ahead?
Okay. Let me see here. Do you see just a slide deck? Okay.
Yep.
Cool. Thank you for organizing this session and all your work on standardization at NASA. This is kind of more or less a continuation of Julius's presentation on harmonizing data formats and standards. It's focusing more towards the virtualized R side of the stack rather than IceChunk, but a lot of the concepts are the same. I have included the logos of some of the organizations housing Virtualize-R core developers, but as Julia said, this is really standing on the shoulders of giants. So in particular, OpenDAP, the HDF group have done so much here in the past, and I'm really grateful for them. I also am, I want to mention that pretty much all of my time on virtualization has been funded on various NASA projects. So I greatly appreciated their support of this technology. And we actually just finished, or maybe this week, are finishing our planning for the next 3 months of work. And one of the objectives that we got approval to work on is the support for variable trunk grids. So that's the question. Like, we're committed to delivering on that feature. I think that quarter ends sometime like April 17th or something. So yeah, stay tuned there. Okay, I'll go over a very brief introduction. I'll try to keep this quick since we did just see Julius kind of give a wonderful overview of some of these concepts. Then share some recent developments, touch on how this connects to enabling standards compliance, and then give some ideas for some next steps. We've pretty much already seen this figure, so but just to recap, Virtualize-R enables harmonized cloud-native access patterns. This makes it easier for users because they don't have to learn, different access mechanisms and workarounds for every single file format and connected to every single interface. It also reduces the amount of software development time needed by data providers because rather than building connectors between every file format and every user interface, you can build a simple parser and get the benefits of cloud-native access patterns with ZAR in a very kind of efficient type of way. And this is from working with one of the data sets that Julius Busecki created, the National Land Data Assimilation Product version 3. And this figure shows how long it takes to open the data cube if you have in region, so compute located in US West 2, using 3 different methods. So the left bar is using FSFEX default configuration, the center bar is using FSFEX block caching, and the right bar is using this virtual ZAR with Virtualize-R and IceChunk. And the reason Julius started working on NLDAS3 was that scientists couldn't even do any sort of time series analyses with the default options. As we see here, it was taking well over 10 minutes to open a data cube representing 5 time steps. And that was kind of made the workflows impossible. By doing a little bit of configuration from FSFEC, which is kind of the first step that we always go to, we brought this down that you could open this small data cube in, just over a minute or so. But it still was not fast enough for them to be able to do their work in a reasonable amount of time. And so Julius built this virtual ZAR store, which opened the data cube in 3 seconds. And I think the really to drive the point home here, this is opening the entire collection of data cubes. So spread over around 8,400 individual files in 3 seconds, where it was taking over a minute to open a data cube representation of just 5 of those files using pre-virtualization approaches. So this is kind of the reason to do this is it makes working with these data on the cloud faster, which directly translate to cheaper because you have less compute time that you're paying for and less data egress that you're paying for. That's pretty much it as what I'm doing for an introduction. I gave a talk on Virtualize-R concepts at ESIP July 2025. I also think that Julius's talk was fantastic, so check out one of those if you want more in-depth introduction. Instead, I'm going to give a brief overview of what's happened since July 2025 when I gave the last ESIP talk on Virtualize-R at Amy's cloud computing session. One of the things that I think is pretty cool is that we've built a lot of new parsers, which are the way to build Virtualize-R data cubes from individual file formats. I built a parser to go from TIFF to Virtualize-R. Sean Harkins wrote a parser to go from the high resolution rapid refresh Noah data product to parse virtual czar, you'll notice that for Grib, I think it's usually better to write data set specific parsers rather than a universal Grib parser, because Grib has such a flexible file format that it would be a very hard API and a very hard development task to write a universal Grib parser. My personal opinion is that dataset dependent, dataset specific parsers are a good model for Grib. Another feature that we just released last night in Virtualize-R 2.3.0 is a new top-level function called Open Virtual Data Tree. In this example, we're virtualizing a TIFF with overviews, and you can see on the right that you get a data tree with each group representing a single resolution of this. And this is just really designed to make it a little bit easier to go to virtual data trees of data cubes. And what I've been kind of most excited about is how many people have been building adoption and demonstration of these virtual data sets, in particular, the data producers doing this. So like the people at Podac and other DACs as part of OpenScapes and Earth Access showing this in practice is just so cool. And I think I 100% agree with Julius that it is like the optimal solution is these virtual data sets being produced by the people who know the data the best and already have the operational workflows to do continuous updates in near real-time data. So how does this relate to enabling standards compliance? When we go from these individual file formats, we not only have data formats that we have to harmonize into ZAR, but also metadata formats that we are needing solutions to harmonize. So NetCDF, kind of the most well-formatted NetCDF files follow CF conventions. Grib, I have absolutely no idea what metadata standards they follow, but I think there probably are some, I hope. And TIFF files usually follow OGC kind of wrapper or kind of stamp on community developed standards like GeoTIFF and Cloud Optimized GeoTIFF. So when you create these virtual ice chunk stores, what do you do? Should you all translate to CF conventions? Should you all translate to TIFF style OGC conventions? Or should the ZAR adapter understand all of these connections as another form of both data format and metadata format harmonization? I don't have the answer to these questions. I think that would be a great thing for us as a community to solve together. But what I have worked on is kind of some community frameworks to allow at least defining what you're doing with your virtual ZAR stores. So in October, we had a ZAR community summit where we worked on this really longstanding issue of when you're using a ZAR data store, how do you define what metadata standard or convention you're using. And out of this, we created a ZAR convention specification, which is essentially the registration mechanism for your metadata standards in a self-describing way. And we prototyped these 3 conventions that were asked for by the Earth observation community in a large part so that the Sentinel reprocessing to ZAR that's ongoing can use a metadata standard, where in contrast to like a kind of hodgepodge solution of different CRS and bounding bots, et cetera, metadata formats. And these are the spatial convention, proj convention, and multiscales convention. I've been working with GeoZar for the last few years to try to build out standardization for geospatial data in ZAR. And we recently have aligned on this vision of GeoZar being comprised of these simple composable pillars, the RZAR conventions, including proj, spatial, and multiscales. In late 2025, we released the ZAR conventions framework and proposals for each one of these individual composable pillars. And with this, I actually just said this 5 minutes before, but I wanted to at least mention tools for compliance with ZAR, with tools for standards compliance. And so far, what we have primarily is a template. So when someone's building out a new convention, they can start with this template. It includes a skeleton for JSON schema, which works well because ZAR is primarily a JSON-based API. And it comes with a simple JavaScript validator, but this schema can be used with any sort of JSON schema validator. And there are JSON schema validators written in most languages along with online tools. But in the future, I think most of our users are Python familiar, and Pydantic ZAR is really the future of ZAR standards compliance because it's a lot more powerful. You get both static and runtime checking. And it can allow better defining the relationship between different entities and metadata standards. So yeah, next steps. How am I doing on time? Do I have a couple minutes left?
Yeah, go ahead. We're informal here, so
okay. I forgot to start the clock. So
go ahead.
Cool.
Yeah.
I think one thing we need is to have an OGC kind of stamp for these GeoZAR conventions. This is something that is in our roadmap. I have volunteered to step up as one of the next two co-chairs for GeoZAR, and we need another person. If anyone is an OGC, part of an OGC member organization and interested in helping with that, that would be huge. For ESCO's roles, I think that building out the ESCO standard for ZAR v3 is an amazing next step. I'm happy to help with that. After that, I think it would be worthwhile to have eventually an ice chunk standard and guidance for how to use the GeoZAR approach. And then yesterday, James Gallagher started a ECIP cloud computing cluster specifically on how to have a chunk manifest standard. My personal opinion is that something like a protocol might be more helpful than a standard because we have a lot of ways to encode it on disk. What we don't have is ways to interchange that information between different libraries and different languages. Another thing that I think hasn't really been worked on yet, but would be huge to work on between now and the next ECIP is guidance for how to have lossless aggregation or coalescence of granule level metadata into data cubes. So here, for example, you have a stack of netcdf files. You go from that to an individual virtual ZAR per granule, and then you go from that to a data cube. But what happens when you have semi-structured or unstructured metadata in each individual file? Do you discard that? Do you only include it in the file in the data cube if it aligns for each granule? We actually do already have a way to handle this because oftentimes the time information for individual granules are encoded as semi-structured text, and we can promote that to an array and have a new time array. I think that this model will work for a lot of different semi-structured textual-based metadata, but having some guidance around that and demonstrations would be really important because currently I think most times this is just actually lost if it's not a time coordinate, if it can't be easily promoted to a time coordinate. And then I think that having more convenient access to this virtual data via CMR and Earth Data Search is huge. I was so impressed by Dean's talk this morning and seeing that PODAC has already done this with a sea surface temperature data set. That's amazing. And I think building out templates, like we built one at VirtualZAR, but I also see that PODAC has templates that might be very useful to have other boilerplate virtualization pipelines on, and popularizing those and improving on them together would be a really important next step. And then there's so many more technical features that still, we have to work on. One is there's been some early demonstrations of orbital swath or L2 level support. I think we might even be hearing about that in a little bit. And I think there's more work that can be done there, in particular, how to have a unified access point to both the data and the metadata and how you update and query that. We also, as I mentioned, are committed to implementing variable trunk grids within the next few months. We have not yet committed to implementing variable compression schemes within an individual array. So if anyone wants to champion that cause, it would be extremely impactful. And then there's improved Earth access integration. You can always have better docs and so much more. So if anyone wants to join this effort, I'd be happy to chat with you and put you in touch with like the proper, like the best Slack channel or best community meeting to get onboarded. And yeah, but thanks again for organizing this and inviting me to talk today.
Awesome. Thank you so much, Max. I still have lots of questions, but does anybody else have questions? I would love to hand it off to Dean now to talk about some work he's done prototyping XAR for level 1 and level 2 data sets, which is something that I know that there's a real need for. Some people at the ASDC have mentioned wanting to be able to do that. So Dean, take it away.
Thanks, Beth. Question. Now that I'm like seeing the flow of these talks, wait, I haven't shared my screen yet. There we go. I almost feel like the presentation that I gave in the previous session, like Bridging Cloud Divide, is like more appropriate. But so I'll ask you all, like, are you more interested in how we at Podac have been integrating virtual data sets, like L2 through L4, like kind of how we create them and serve them currently, that overall ecosystem? Or are you more interested in specifically how we've prototyped some L2 collections? Or I can touch on both, but in just less detail.
So, Dean, I'll tell you for myself, I am really interested in, how we do this at the ESDIS level in a sustainable and scalable way. I was curious to ask Max and Julius this question because some years ago I was working on a project where we needed to parse HDF and NetCDF files. It was to extract variable data, to subset variables from the files. But the parsing, somewhat to my surprise, I discovered that around NASA, and this was years ago, so maybe things have changed a lot, but around NASA, almost every mission and sometimes every data product within a mission had its own parser, its own bespoke parser, because we couldn't parse a random HDF NetCDF file. And so one of the things I wanted to tee up for a discussion later, and Dean, I don't know if this answers your question at all about how to proceed, but I am really interested in this problem about how, if this involves parsing files, how are you overcoming that problem of all of these crazy, radically different data models that make it really hard to just parse a random file that's, like if I just want to grab any old data product and send files to be parsed. Is that something that's part of either of your talks?
I can show you what we've done so far. So our solution to that so far is that we've integrated into our ecosystem like the better behaved data sets, just showing the proof of concept of how this could all look. And then I think from Podac's perspective, we've shown proof of concept, and then whenever someone asks can you deal with this more complicated data set? I'm always kind of like, Max and Julius will figure that out at some point.
Okay. Great.
Appreciate you guys heavily.
Glad to know it. Yeah. So anyway, that's my 2 cents, Dean. I don't know if that helps you, but others should weigh in here on what they want to hear about, and or do whatever feels right to you, Dean, and then we can have a free for all later where people can talk about whatever they want. So
I'm gonna in that case, I am gonna move my slides around a little bit and give more of an overview of the overall ecosystem, but then also touch on the L2. But yeah, that's a good way of mentioning that, yeah, we are very appreciative of like the Earth Mover and Virtualizer folks. They're the ones like pushing this forward, and we get to use the technology at Podax. So I'm going to start off by talking about how, right? So Julius and Max have been talking about IceChunk and Virtualizer and how this would look at a DAC. And so we've developed a way that it could look at a DAC. So I want to go through that. So this is the high level overview schematic of, so we first we create the virtual data sets, and we create it for the entire data set as a whole, right? There was talk about like individual, like virtual data sets for individual files versus the entire collection. We've gone with the entire collection because it's easiest. And once we have that, we store that in a Podax public bucket. It's not the same bucket that we host the native NetCDF or HDF files on. It's a different bucket that's like devoted to virtual data sets. And once it's there, then we link to its location in the bucket, since it's just like a single, file location that we need. We link to that location in the UMMC record. We found this related URL type that we could use that I'll talk about in a moment. But yeah, we store that in the UMMC, and then from there, it's easy for either Earth Access or anything that queries CMR to check whether or not a collection has a virtual data set associated with it and find the link to that and open it. And so I'll talk about that in a little bit more detail. So I'll skip, I think, well, it's not in here. It would have been in my other presentation, the actual generation of these virtual data sets. But know that if you contact me, we have publicly available like example workflows of how we're generating these in Python. But in CMR, this is the entry we found. So there actually is, if you go under like distribution URL get data, there is actually a virtual collection field that already exists. And so we put that into CMR. And once we do that, here's an example from the new Earth data like landing pages for one of our, this is for the level 2 wind data set that we made a virtual data set for. But if you hit data access, you'll actually see automatically virtual collections show up there. And this is the link to the virtual data set reference file. This happens automatically, right? Since we've populated the UMMC record. So, and then from there, as far as like a user actually using it, if they, go to a dataset landing page, copy this URL, and then, put it into their Python script or their Jupyter notebook. And then there's a little built-in function that we have them currently copy and paste into their function called getVDSMapper. They don't got to change anything about it, but, you put your virtual dataset link into this function and you get a virtual dataset mapper, and that goes straight into Xarray Open Dataset. And then from there, right, you've opened the entire data set. In this case, it's 13,000 timestamps. I forget how many. It's like almost a terabyte. But this is what it looks like. And further, like in the future, right, this getVDSMapper would be wrapped in the Earth Access package, so it wouldn't be even a function that they have to copy and paste themselves. But this is, Beth, I hope this is getting kind of to the point of like the homogenizing the heterogeneity across all the data sets that you see. We would like, as long as we figured out how to create a collection level virtual data set and we provide them a link, and then Earth Access can open it, get the mapper and hand it off to Xarray. These three lines of code look pretty much identical regardless of the data set you're dealing with. And then you really are dealing with data set level stuff. Now the dimensions within those data sets obviously are going to be different, but this is the overall workflow. All right, so that's what I'm going to go over as far as like the general, and we've done that for 10 level 3, level 4 collections so far. Those are all available, and you can find them on their respective like dataset landing pages. And on our cookbook chapter devoted to virtual data sets, which I linked to here. And then we do one level 2 data set. And so that's what I'll focus on for the rest of this talk, and how we've tried to tackle that. So challenging aspects of level 2 data sets, you probably all already know, but I'll just list them out. So there's no uniform spatial coverage, right? These are the outlines for different satellite swaths, like orbits, for each of the successive granules. Dimensions are not latitude, longitude. And so it's like, what's the intuitive way to actually create this virtual data cube? And then another thing that I should have added, right? Because so for some of the newer projects where like the pastimes of the satellite are like perfectly overlap, after a certain amount of time, that's not the case for kind of some of the older L2 data sets. So this one that I'm showing here, this is a scatterometer data set where I was told by the data producer, no, you cannot like align by like orbit and pass number. Like that won't work because there's too much drift. So I tried a few things, or we all tried a few things at PODAC. The first was to just concatenate along the along track dimension. So you can imagine, right, if you follow my mouse, right, this is the orbit of one granule, and where that ends, the orbit of the next granule starts, right? So what if you just strung those all together, concatenated all the granules that way? It would be almost like if the satellite just kept like dumping the data as it orbits into the same file, and just that along track dimension just keeps growing. And then the other two ways I tried they're kind of similar in that you're just concatenating, you're smashing all the files together along a new dummy dimension. But in one case, the dummy dimension is kind of like a pseudo time dimension where I use the granule start time for each of the coordinate values for each dimension of the value. Sorry, that did not make any sense. For each like entry of the dimension. And then another one is just the granule ID. But the same idea where it's a dummy, concatenating along a dummy dimension. And so I can share these slides somewhere so people can like look at this in more detail. But the long story short was that concatenating along the dummy time dimension seemed to be the best balance of the pros and cons that we experienced. I'll just touch briefly along what the issue with concatenating along the along track dimension was, because that one seems like a pretty intuitive way to do this. And what we found there is that because you actually save, I can go into that in more detail if in the discussion, but long story short is that the virtual data set itself, when you concatenate along that dimension, becomes cumbersomely big. And I can touch on that in the discussion. But anyway, so we went with concatenating along a dummy time dimension. And so the workflow kind of looks like this. So we search for the UMMG records using Earth Access. We get the both the URLs, the S3 endpoints to the granules, as well as the granule start times. And so we save the granule start times for each granule, as well as make the virtual dataset reference files for each granule. Of course, the individual reference files are then combined into this combined virtual data set. And then when we've combined them by concatenating along a dummy time dimension. And then in the process of creating this combined record, we also assign to this orbit segment start time the granule start times that we've extracted from the UMMGs. So this would be start time 1, start time 2, start time 3. So if you are not following, I don't blame you. This is the first time I've ever truly tried to like present this information, and I'm sure I'll have to do it a few more times before I do it well. But so we've done this for one collection so far. It's a very modest collection, but start with the low hanging fruit to make sure things work. This is a wind data scatterometer collection. It's about a terabyte. It's got 13,000 granules, 1 orbit per granule. It doesn't take long to generate these. It took like 15 minutes to create this combined reference file using 15 small VMs in parallel. And I have a link to the workflow that we use to generate that. I already went over these slides. It's the more general, like how virtual data sets fit into our ecosystem. But what I want to touch on, again, is like how the user then interacts with this. How is this actually like a useful way of creating a combined level 2 virtual data set? So this is opening it, as I showed before. Once you have the virtual data set link, easy to open it. And then the two big things that I see, like the baseline utilities that you need to have if you're going to say like successful virtual data set or virtual data cube, is that you need to be able to do like spatial and temporal like search and subset, right, within that data cube. So temporal subsetting is very simple, right? It's right. We've concatenated all these level 2 granules along a time dimension that we called orbit segment start time. And so, right, you just have a start time and an end time, and then use, Xarray built-in syntax to slice along that dimension. And you can see that now you've got that slice of the data set, right? Originally it was 13,000 files, and you've narrowed it down to the 4,400 files. That one's straightforward. The spatial search and subset is more difficult, and I feel like that's always kind of been the issue with level 2 data sets. It's kind of why you have level 3 data sets. And so we go about this in a roundabout way. It takes more lines of code, but it does work. And the way we do that is we actually kind of combine the powers of Earth Access plus CMR, like granule searching, with this data set we've created. So the workflow would go like this, or it does go like this. This is actual code that works. So you specify your bounding box, and then you search for all granules that fall within that bounding box using Earth Access. From there, you extract the granule start times, and that's just 2 lines of code, and even that could be absorbed into Earth Access at some point. And since our virtual data set is concatenated along granule start time, these granule start times that you've extracted from the UMGs that fall within the bounding box can be put right into the virtual data set, using Xarray syntax to select along the time dimension to find all those granules that fall within a bounding box. And so I plot out the first few time steps that you get, and this red box is the bounding box. And so it's confirming that, all the time steps that you're getting have orbits with data within the bounding box. So this does spatial search. It doesn't do spatial subset. I went with this because we talked with a project scientist who said, if you get me to this step where you've at least narrowed down all of the time steps that have data within the region of my interest, and they're all like concatenated along this dummy time dimension, I am happy to write my own code, like my own for loop, to go through each of these and do whatever analysis that I want to do on that. That's why we chose that. So I feel like I've been talking for so long that I don't want to even throw even more challenges. There's obviously more challenges, and we can talk about it during the discussion, but I'm going to stop there and see if anyone has questions or if we just want to move on.
Thank you, Dean. This is really interesting. And I think, Julius, you put a comment about having a similar problem in a use case you encountered. So that sounds like there's lots of stuff here for some kind of working group. We need a czar working group, you guys. I think it sounds like this is really interesting. Are there questions from anybody that need immediate answers? Because I would like to turn to Owen to talk about some Harmony services that we have. So that concludes our czar portion of this session, I think. We will, if
Something
there's
completely
time.
different.
Yeah, if there's time, Max has his hand up. Sorry, Max. Go ahead.
I actually, if you don't mind, I just have one comment before we turn off czar for the day, which is totally fair.
Of course.
I don't think it's meant to be exclusive in any way. So Amy Barchowskis started organizing virtual stores co-working sessions that are every 2 weeks. And I think that more or less is a virtual czar working group. So if anyone is interested, and is working on this stuff.
Yeah.
Okay. I'll put you in touch. And then I think the ESIP Slack, a DM to Amy is probably the, if you don't want to rely on me on remembering to introduce you to Amy, then just reach out to Amy directly on
That's
ESIP.
great to know. I won't join that working group, but I would like to pass this along to others that I think would really want to participate in this. So yeah, I think this.
Thanks for letting me delay the next.
This has been really great and helpful, I think, for us. I mean, czar, just to circle back to ESCO for a second, czar is the cloud optimized storage standard that has been adopted by ESIP. And I think, hearing about how people are using it and what some of the challenges are and figuring out how to address those challenges is really valuable. So thank you all for that great material on czar. We're going to turn to Owen. He's going to talk about some of the Harmony services that the ESDIS EED team has developed for doing a variety of things to data that aren't necessarily czar. So, but are also very useful and interesting. So go ahead, Owen.
Yeah, sure. Thanks, Beth. For folks who don't know me, I'm Owen Littlejohns. I'm on the NASA EED3. Sorry, I can see a big thing of my own face, and that's very off-putting. Let me just move that down.
I know, I hate that.
But yeah, I'm on the NASA EED3 contract. I'm on the transformation train, which to make sure I sort of give everyone the right credit, it's not just EED. We also have teams of the various DACs working on various transformation services. And one of the big places we kind of converge together on that is a thing called Harmony, which is essentially a workflow orchestration engine and API. The idea being that hopefully end users from with experience using different data products can make requests through the same API and sort of have this kind of standardized interface, regardless of whether they're trying to get sea surface temperature information or, wind speed, or I'm blanking on other scientific measurements, but the idea being it's consistent and easy to use for as many possible people. I think a big piece of this as well, and this kind of maybe goes back to some of the things that both Julius and Max were saying earlier on. There's this idea of sort of shifting effort upstream, and so at the moment we're not heavily using czar. There's prototyping work to try and use virtual data stores ongoing, but a lot of it has been interacting with actual native data within the archive, and so there's kind of this. It's like a Boy Scout approach type thing where, we get all these various inputs from the archive, and what we're putting out, we're trying to make sure is compatible with the sort of tools that end users or even internal users have and need and are trying to sort of integrate with those outputs. So, things like Panoply, QGIS, ArcGIS, the Pangeo suite of tools, so things like Xarray, kind of the benchmark of whether these services are successful is, can people use those tools with the output of our services? And so I kind of want to talk maybe quickly about sort of 2 or 3 little things. I don't have slides because I didn't sort of put them together in time, so apologies for that. But I might try and screen share a couple of web pages to just, not have you all looking at my face for the next couple of minutes.
To be clear, I did not ask Owen in time to get slides together, so it's totally not his fault that he doesn't didn't put them together in time.
Thanks, Beth, for covering me there. Can you see my screen? Hopefully, big blue thing saying Harmony and stuff like that.
We can see it.
Okay, great. So just for anyone who hasn't really heard about Harmony before, if you want to know more, harmony.earthdata.nasa.gov is a good place to go. There's a whole bunch of documentation on how to use the API. I'm not going to go through that now. The other thing is, if like me, you're more of a Python person and sort of programmatic access is your game, Harmony Pi, which is a package published on PyPy, that's a really good way to go. A lot of the services that we have documentation, Jupyter notebooks within the repos themselves, so you can really see how to use these things in practice. But where I really want to sort of start with, I think first, is a thing called Earth Data VAR Info. This isn't a service in and of itself. It's a Python package. Again, it's available on PyPy. The idea here is that in a lot of services, we found there's this step of parsing a file. NetCDF4, HDF5 is primarily the focus of this package. And sometimes the data aren't quite how we would like them to be. Maybe there's sort of a mistake in the processing. Maybe a fill value is incorrectly put in the metadata attributes. I don't know, other examples like that. And so the original premise behind this Python package was it would be great if when we open that file, we had some sort of standardized mechanism to say, okay, well, we know that actually, the fill value is actually 100 rather than 50. And so this is our sort of standardized package that's shared across a whole bunch of different Harmony backend services, trying to sort of take away the burden of repeating that same sort of cleaning step across multiple places. Another part of this, sort of a dream that maybe we haven't quite realized, is the way that these services know for product X, this metadata attribute might need to be updated, is that we have a sort of JSON schema defined configuration file. I'm just going to hop over to an example that we have in the repo. I'm going to scroll down a little bit. And essentially, the idea was if we have these well-defined things that say, hey, let's see this, for the SMAP level 4 products, we think that the grid mapping attribute, this is the grid mapping attribute should have this value for all of the variables. And there are other things in here, like, for example, the global projection variable should have all of these attributes with all of these values. And so having those not only means that we could, in theory, use this information across lots of services, but the bit that we haven't closed the loop on is maybe passing that back to the data producers and say, hey, these are some teething issues we had. Maybe when the next version of this product comes out, you could take into account what we found here. And by the way, this is an easy way for hopefully you to digest it. So there's some improvement there to maybe be had, but that's the sort of the grand plan there. We've also maybe gone one step further, as sort of thinking more going upstream, instead of perhaps having to have all these different services still sort of pass around these configuration files and call the Earth Data VAR Info package. We've created essentially a Harmony backend service that encapsulates this mechanism. And so, Harmony itself calls things in a series of steps. And so early in the chain, for a lot of these service chains, we call a service that's entire purpose is basically to apply these metadata corrections to the files and then pass that corrected file on downstream. So in that case, those downstream services, they don't have to care because things have gotten to them as would be helpful. So those are two of the things I wanted to talk about. Another one, which is sort of less end user facing. It's more about some of the internal processes we've started supporting and trying to standardize around. So I don't know how many people have heard the phrase HiBig or Imaginator or things like that, but essentially we have this whole bunch of data, and often when those sort of files are ingested, the data providers want to produce browse imagery that can then be hosted in Gibbs, and then things like Worldview can display that browse imagery, and it gives like that really nice, easy visual entry point for a lot of users, particularly ones that maybe aren't so sort of savvy with Python and just want to see what the data look like and say, okay, yeah, I can see this hurricane. Like I should probably download that file. And so historically, there's been a lot of siloed sort of processes to try and make that browse imagery, and the aim is to try and make that easier, particularly for say new missions coming on board where perhaps they don't have the expertise to do that browse image generation. Maybe they don't know the Gibbs specification very well, and so the aim has been to provide this pipeline that folks can use and just say, hey, here's my data product, please make me a Gibbs compatible browse image. And so just to sort of some of those words I threw out there earlier that were a bit buzzwordy, there's a thing called Big and Bit, which is a PODAC maintained Cumulus task. So Cumulus being our ingest workflow engine, which essentially it receives the notification that, hey, there's this new thing being ingested. And that itself calls Harmony. So that's why I have anything to say about it. And then within Harmony, we have a thing called Imaginator. I cannot remember the full definition of that acronym, but it's a service chain that does a number of steps to sort of take that source image data file and create a Gibbs compatible browse image. So there's a step that can do things like filtering. So perhaps the browse image that you want. Maybe you want to make sure that values are capped at a certain maximum or minimum, just sort of kind of sanitization of the image that you produce. There's steps to convert, say, level 2 into level 3 data so that it's easier to then convert into a COG. There's a step that can convert netcdf4 files into COGs. It's called net2cog. That's another PODAC service. And then there's another sort of step in that chain called HiBig, which is the Harmony Browse Image Generator. And that's really that final step of, hey, I've got a cloud optimized GeoTIFF, and I want to get something that goes into Gibbs, and I want it to sort of, have the right resolution. I want it to be in the right projection, all of those good kind of things. And so that last step will produce that. And then going all the way back up to Big and Bit, it sort of takes that browse image and then says, hey, Gibbs, I'm ready for you to look at this and see if it works. So there's a lot of sort of sausage making maybe in that description, but the main takeaway here is we're trying to sort of standardize around, a single pipeline is probably not going to be perfect for every collection, but for sort of those easy collections that we can, let's, avoid having to reinvent the wheel to get browse imagery into Gibbs and therefore, visible in Worldview. And it seems to be working pretty well. Actually, the interesting thing over the last 6 to 9 months is that before we were really doing any browse image generation, we had, I think it was something like 50 to 60,000 requests to Harmony every month. And, that was end users doing subsetting, reprojection, all that good stuff. Now that we're starting to generate browse imagery through Harmony, that's rocketed up to something like 1.5 million requests to Harmony every month. And that's predominantly for the Opera products that both PODAC and ASF are supporting. And so it's actually been a fantastic load test of our system to show that we can support that scale of requests over a month. But yeah, it's been working well. I think generally sort of that idea of shifting things to the left has been successful. With that service chain, for example, with generating browse imagery, it's taking away some of the burden on the data providers from having to understand exactly what it is Gibbs needs. That's, I think, a big win. I have a data product, please make me something that works with Gibbs. And, that's been pretty successful. And so I don't know if the future is for Harmony to continue being the place where these things are generated, but certainly the code that Harmony is using, I think, is the basis of something in the future. And maybe it gets shifted even further to the left. I don't know, but it feels like a good step. And yeah, it's been pretty successful so far. So I think that's all I wanted to ramble about there, Beth. Thank you.
Thank you, Owen. Y'all, I have so many thoughts, but sadly, we are almost out of time. So I'm going to keep my thoughts to myself for right now. Shannon, I know I think you're still on. I was hoping that we were going to be able to talk about the role of metadata in making some of these things work. And I'm really interested because I know Owen also said, well, the easy collections, we'll do it with those. And I know we're always sort of working on these easy collections. I really hope we can have some kind of follow-up at some point where we are able to talk about what we need to do with our metadata to make these things work across a larger swath of NASA data and maybe other data. I was hoping that we could talk about Stack and what we need to do with that. So sorry, it's all just so interesting and there's so much to talk about and we just don't have time. I was hoping to talk about variable level metadata and I'm not going to do it because don't even get me started. You would not get away in time or you would all have to just leave me talking to myself. So I'm not going to start down that path right now, but this is, I really appreciate all of you guys. All of your presentations have been really helpful and I want to know more about Czar and how it works and what those data cubes actually look like. And all kinds of things. I want to know so much. I'm going to stop here. We have 4 minutes. Does anybody have anything they want to say or ask or? All right. I will, in that case, I'll blather on about metadata for a second. Shannon Leslie, who's here in the meeting right now, is the lead of the metadata stewardship team. And I just want to mention that she's here and that she's leading this team whose job it is to, help improve the metadata for NASA data products. And I am really curious, if you guys, the development side of this, if there are metadata related issues that would be helpful in implementing or making these things work more broadly. I have this suspicion that there are, and so I wanted, I want us talking to each other. One of my goals here is that those of us who do data curation and metadata curation and that kind of thing, have more conversations with those of you who are developing tools and services for data, because often, these things get done in completely separate worlds, and I think that we could help each other. So that's, I think, all I've got to say here. Shannon, do you want to add anything about metadata? I'm totally putting Shannon on the spot.
This session has been incredibly informative, and I will say, I think a lot of the focus here is sort of the sort of science file embedded metadata. I would sort of call that, as opposed to some of the sort of what I differentiate as kind of the sidecar metadata stored in CMR that has been sort of the focus of the metadata stewardship team to date. That's not to say we couldn't shift focus, but we'll be talking. I'll just put a plug in a bit about the team, the metadata stewardship team, tomorrow on the ESDIS session. So, but really interesting talks.
Excellent. Yeah. Steve, any last thoughts before we end the meeting?
I'll keep it brief because a contractor just started drilling above me. So, but no, interesting talks. Beth, I think there's more we need to cover here, and maybe we should be thinking about a session for the summer meeting.
Definitely. There's so much more to say, and I feel
Right.
like, we barely scratched the surface here.
Yeah. So definitely interested in continuing this discussion.
Yeah. But thank you so much, guys. I mean, I know that, these standards are going to really go a long way toward making our data more usable. So we're really grateful to all the work y'all are doing.